Hello, everybody, and good evening. We're going to finish up our official collaboration with MATHCOUNTS for their state target round today. The state competition is the last round of the MATHCOUNTS before deciding who goes to the national competition. I guess that would make sense. And it's often quite challenging because these are where the top math contest students from every state come together. We just did the sprint round in the last two sessions, and those were quite hard, actually, for me to think through as well. We took 2 hours to do the problems, and the MATHCOUNTS state sprint round, you're supposed to have only 40 minutes. I have enormous respect for the people who are doing these competitions. Now, today, I want to emphasize, just like last time, that these are an official collaboration with MATHCOUNTS, and so what that means is that we're using their official problems, but the problems are copyrighted, so please don't just copy the problems elsewhere. This particular collaboration was officially sanctioned by them, and it's a real honor and pleasure to be able to do that. All right, well, let's go ahead and start discussing. I'm just going to go and see. I want to make sure that I can see all of your feedbacks and comments just as they're coming in. All right, well, we're going to do the target round now. In the target round, what you get is you get 2 questions at a time, and you have 6 minutes to do each pair of questions. Here, we're just going to do the problems, okay? So we're going to do these 8 problems. They come in 4 pairs of 2, and we're going to try to do these 8 questions in this 1 hour. And the first question is, if A, B, and C represent the distinct numbers 1, 2, and 3 in some order, what is the greatest possible value of the expression 817 times A plus 512 times B plus 210 times C? Okay. So I have these 3 numbers, 1, 2, and 3, and they're in some order. Well, the way these things work is, if you think about it, when you're trying to multiply things together, the A, the B, and the C, you can almost think of it as saying, I'll be able to get 3 of something, 2 of something, and 1 of something. Well, I'm greedy. I want 3 of the biggest thing, right? If I want to make this as big as possible, and someone's telling you, hey, you can get 817 points, 512 points, or 210 points. You can choose which one you want 3 of, which one you want 2 of, and which one you want 1 of. Well, obviously, I want 3 of the biggest one. I'm a greedy person. So the greatest possible would be to put 3 on the 817, and then 2 on the 512, and then 1 on the 210. So that would be probably the answer. And that's an easy way to think of it too, right? It's like I'm going to go and get 3 of something, 2 of something, and 1 of something, and want the most, make sure you get the most of the most. And this is actually part of an inequality as well. You could prove this. Well, I mean, I just went through the intuitive proof. I pulled this up because in MATHCOUNTS for the target round, you get a calculator. And if you have noticed from all of the teachings that I've done, I'm actually not a calculator myself. We use calculators for that. Where is the calculator? I just got a different phone. Okay, here we go. Calculator. So I want to do 817 times 3, okay, plus 512 times 2. Oh, I know what that is. That's 1024, because that's a power of 2, plus 210 equals 3685 is the answer I got. Let's put this down. So I'm getting 3685. And that's the answer that I'm going to propose. Let's see if this is correct. Yes, that is correct. Somebody said nice iPhone 7. I mean, I'm just using some kind of it's actually an iPhone 8. Nowadays, I've been working on some app to try to stop the spread of disease, and we've been testing it on all of these different phones. Okay, let's continue on. Question number 2. A year ago, Karen grew some popcorn. She removed kernels from the cob and put them in containers. She had 14 containers, each holding 6 pounds, 9 5/8 ounces, and one container holding 4 pounds, 7 3/4 ounces. In all, she had X pounds, Y ounces of popcorn kernels. If Y is less than 16, what is the value of X plus Y? Okay, so it's just saying I need the whole thing in pounds and ounces. What's the fastest way to do this? Okay, so I'm going to tell you, I see this as a question where I need to know about pounds and I need to know about ounces, and I need to do lots of multiplications, right? So I need to do 6 containers. No, there were 14 containers. 14 containers, and each of the 14 containers is 6 pounds, 9 and 5/8 ounces. Ounces is OZ. And I'm just writing down what I've got. And I have one container which has 4 pounds and 7 3/4 ounces. I always want to make sure I read the question right. So there's 14 containers of something. Okay. And then there's one container of something. Okay. So I just need to go put all this stuff together. That seems reasonable. So I need to see how many pounds I've gotten all together. That's 14 times 6. Again, you see I'm a lazy guy. If I need to do 14 times 6, here's how I'll do it. I'll take 2 out of the 14 to make it 12 because I know my 12 times table. So I have 7 times 12. That's 84. 84 plus 4 is 88 pounds. I'm lazy because I'm too lazy to pull that calculator out of my pocket. And then how many ounces? Oh, no. Now I need to pull it out of my pocket. Okay, so here goes. So I need to go and actually do this, punching it into the calculator. I need to do 14 times that. By the way, 5/8 is 0.625. It's kind of nice. 1/8 is 0.125, and 5/8 is 5 times that. It's 0.625. And by the way, 625 is 5 to the power 4. 125 is 5 to the power 3. All of these numbers are nice. So I need to do up here 14 times, clear this out, 14 times, I'm going to multiply it by 9.625, 9.625, okay, and then I need to add 7 3/4, that's 7.75, plus 7.75 equals 142.5. The question asked for decimals anyway. But it says we have to be a little bit careful because I need to go and convert this. I need to pull it down, like get rid of it and turn it into just pounds, right? So, oh, just a second. Somebody said 14 times 6 is 84. It is, and that's why I added 4 and got 88. So that's what we have here. Somebody said their calculator multiplies whole numbers by mixed numbers, so it's pretty cool. Good for you. I'm just using the like really basic phone calculator here. But now I need to go and turn this thing into the thing with just pounds. The easiest way to do that is to just use your calculator. 142.5 divided by 12. 142.5 divided by, not 12, 16. There's 16 ounces in a pound. Okay? And that's 8.9 something. That tells me that it breaks into 8 pounds and something. Well, and something, I'll just say, oh, I know what that is. 8 times 16, that's a power of 2. So that's going to give you 128. So I need to do 142.5 minus 128. 142.5 minus 128. You see, I have these various powers of numbers in my head. It saves me work. And here I wanted 8 times 16. 8's a power of a 2. 16's a power of a 2. I'll get a power of 2, which is real close to this, which has to be 128. 14.5 ounces. Great. To finish this, I need to do 88 plus 8. That's going to be the number of pounds total. That's the x. And the y is going to be, well, this 14.5. So my answer is going to be the x is this, plus the y is that. I need to know x plus y. So add everything up. So I need to do 88 plus 8. That's 96. So 96 plus 14.5, what is that? The answer is 96 plus 14.5, again, I'm too lazy to type it into my calculator, 0.5, 6 and 4 is 10, and it looks like we have 110.5, and that's the answer I'm going to propose. Let's see if that's right. 110.5. Yay, it is. I'm always scared of calculation because I might do it wrong. Question number 3. Mira's parents planted an apple tree when she was born. In the year Mira turned 8 years old, the tree started bearing fruit. That year there were 48 apples. The number of apples increased by 50% every year after that. How many apples grew on the tree in the year Mira turned 12 years old? Okay, so when you increase by 50%, that means that you multiply by 1.5 or that you multiply by 3 over 2. So it is in the year when she turned 8 years old, there were 48 apples. Okay? And now the question is, how many times do I multiply by 3 over 2? Because that's the gain of 50%. Well, if I'm going from the year she turned 8 to the year she turned 12, both say the year she turned. Therefore, the amount of years that happened was 4 years of passage of time. So I raised this to the power 4. That's actually how I often think of this. I'm just like, I see the same word, 8, the same word, 12. And that means that the time difference between them is just the difference between those numbers. And that's how many years. And every single year, it grows by 50%. So now let's just go and do this. So that's going to be 48 times 3 to the 4th is 81, divided by 2 to the 4th is 16. I actually recognized that 48 happens to be a multiple of 16. It's 16 times 3. Oh, how nice. This is going to be another power of 3, 243. I mean, not like we had a power of 3 earlier, but we had powers everywhere. So I think that the answer is just 3 to the power 5th. 3 to the power 5, which is 243. And it's good. Question 4. Right triangle ABC has AB equals AC, both of which are 6 centimeters. Circular arcs are drawn with centers at A, B, and C, so that the arc centered at A is tangent to side BC, it sure is, and so that the arcs centered at B and C are tangent to the arc centered at A, as shown. Yes, so it goes up to that point. Now it asks, what is the area of the shaded region inside triangle ABC, but outside of the outside of the 3 arcs? Express your answer as a decimal to the nearest hundredth. Okay, so I know the area of the triangle. That's the easy part. It's 6 and 6, right? So the whole area we'll do later. But for the time being, I need to go and figure out what's the deal with these funny circles. Well, here's what I'll do. First of all, whenever you have a tangency, that means that I could draw a radius. And now, how long is that thing? Well, if this whole thing is 6, there's a 45 degree, 90 degree right triangle going on here. And so if this is 6, this piece is 6 divided by the square root of 2, because the ratio is this is square root of 2 and that's 1. So if I divide 6 by root 2, quick scratch work, 6 divided by square root 2, that's equal to, multiply top and bottom by the same thing, and that's 6 root 2 over 2, which is 3 root 2. Aha. So now I know the radius is 3 root 2. And that also happens to be this part here. So that means that this part here is 6 minus of that. So this part is 6 minus 3 root 2, because this part is also 3 root 2. Now we've got it. I'm first going to write down the big computation we have to do, and then punch things in the calculator. So I need to go and take the area of the whole triangle, which is half base times height. Half of the base is 3. 3 times the height is 18. Then I need to subtract off the areas of these circles. Well, here's a quarter circle. So it's 1/4 of pi times r squared, which is 3 root 2 squared. Okay? And then I also have to worry about this. But this is 1/8 of a circle plus 1/8 of a circle. It's 1/4 of a circle. So minus 1/4 of pi times the other thing. 6 minus 3 root 2 squared. Okay, so what's the easiest way to do this? I need to do this to the nearest hundredth. I can actually go and type the whole thing. Wow, I might need to know a little bit about pi. Just a second. So I'm wondering how many digits of pi I'll need for this. Possibly a bunch. Well, let's go and simplify some of this stuff, right? So this thing is easier. And of course, actually, you could just straight up use a calculator and punch the whole thing. Actually, that's probably what I'd recommend. All right, calculator time. Because the reason is if you try to simplify too many things here, at this point, you're better off just using the calculator. At this point, I sincerely regret using one of these like very, very weak calculators. Because this guy, I just turned it into a scientific calculator. That's cool. Okay, now I'm going to use a scientific calculator. So I need to go and subtract all this stuff, right? So I'm just typing it in. It's like 18 minus how much? Well, I need to do pi over 4. Is there a pi on this thing? Yes, there is. Minus pi divided by 4, and then times the 3 root 2 squared. I'm actually going to just simplify. That's going to be 9 times 2, which is 18. Okay. And I need to continue to subtract something. Minus another pi divided by 4. Pi divided by 4 times, and then I'll do a parentheses, open parentheses. I need to do 6 minus 3 root 2. 6 minus 3 times the square root of 2. Oh no, this calculator is really annoying. When you press the square root button, so I just lost all my stuff. Sorry, I'm going to go back again. So unfortunately, with the calculator I'm using on this phone, it's very, very complicated because you can't like undo. You guys are using much more sophisticated calculators, thankfully. So I'm actually going to do this. The answer is supposed to be decimal to the nearest hundredth, so if I calculate each thing to the nearest thousandth, I'm okay. Because my calculator is too easy to mess up. So this is pi divided by 4. All right, we'll do each one. Pi divided by 4 times, that was 18. Okay, that was 18, equals, so where's my pen? All right, so each of these individual things, and you can see how I'm trying to be careful, because it's very, very easy, because of order of operations, to get things wrong. So this is 14.1372. That should be enough digits. And I'm comfortable writing these because I'm subtracting. If I started doing multiplications, I would be a little bit curious what happens at the nearest hundredth. But here, I take this number minus that number. If I see that the nearest hundredth is sensitive because of the nearest thousandth, I'll be more careful. But now, I do believe the 14, by the way. It does look like 14 compared to 18. As for the other piece is pi divided by 4 times, open parentheses, 6 minus. Now I've learned my lesson. I do 3 times 2, but then I hit the square root button. Okay, great, close parentheses, and then you square the whole thing. Bam! And what's that equal to? That's equal to, this puts it down to be 2.4256. And that also looks believable, okay? Now, what I'll do next is I actually have to go and combine everything. So I have to go and say 18 minus 14.1372, and I sincerely regret not bringing a better calculator, minus 2.4256 equals, okay, finally, the answer. 1.44 is the answer that I'm getting here, at least according to my calculator. Man, you can see I hate problems with calculators. Nothing against MathCounts. You guys are great, but I just am a lazy guy. I don't like punching numbers in calculators. Let's see if we got it. Oh, good. Okay, good. Let's go on. Next question. Question 5. Hopefully we won't need a calculator. Some numbers are hidden in this sequence of positive integers, which contains each integer from 1 to 13 exactly once. Every term after the first term is 1 more than the previous term, 2 more than the previous term, or 3 less than the previous term. Ooh, tricky. What is the product of the two numbers represented by A and B? Okay. So now I need to say, how could I possibly get from 1 to 6? So in order to get from 1 to 6, that's a plus 5. How do you get the plus 5 in 1, 2, 3 steps? If I'm allowed to make 3 steps and I need to grow by 5, oh, this contains all the numbers from 1 to 13 exactly once. Wow, this is tricky. What I'm seeing here is also there are ways to go down. So I'm just trying to think through the whole thing. Here from the 6 to the 7, I've not made much progress going up. But what I'm seeing is that, I should probably, here's what I'm going to say. I should probably grab the plus 1 first. Because remember, I said I'm going by 5 total in 3 steps. And I can make that out of plus 1s, plus 2s, and, well, minus 3s. I'm not going to use those. So it's going to be 1 plus 1 and 2 plus 2s. But I'm seeing here from the 6 to the 7, I need to do something close to the 6 and the, I'll probably need to go back some. And so I don't think I'll go back all the way to the 2. So I'll grab the 2 now and now do a plus 2 and a plus 2. So I think I'll do 2, 4, 6. So this is my sequence so far. Now I need to go back and fill the things I missed. So I'm going to go back 6 minus 3. That goes to 3. Plus 2 is 5, plus 2 is 7. I'm very happy because, you see, with this kind of going forward and back, I'm using every number exactly once. And that's how I knew that the first one I should do a plus 1 and then the plus 2s. Because otherwise I wouldn't be able to figure out how exactly do I go from the 6 to the 7. And that's my last chance to rescue a few small numbers. All right, how about the rest? Well, the rest, I have the numbers from 1 to 13. So, okay, over here probably I'm also going to dip down low and then add some more. In particular, oh, interesting. If I look at this thing, if I need to go by a plus 1 total, and I do 1, 2, 3 steps, I can't do that with a minus 3 and then a minus 3. I'll never catch up. So I need to do a single minus 3 and 2 plus 2s. So my guess is that this is going to go 9, 11, 13. I decided to look at the end right away because I just saw two numbers consecutive and I just did something there. Okay, let's see if the rest works. So from 7, hey, it looks like the same pattern again. So I bet I go by +1 and then the +2 thing. So it's +1 and then the +2 thing. I think it works. We got it. We got all of the numbers from 1 to 13. We have everything exactly once. We always went by +1, +2, or -3. And we want to know the product of the numbers represented by A and B. 4 times 8 is 32. I don't need a calculator for that. Hooray. Okay, so I'm going to put this 32 here, right? Is that what I wanted? The product of the numbers represented by the A and the B. 4 times 8 is 32. Okay. Yes, and we're good. I saw some people in the chat said it's 12. I hope that maybe what you were referring to is like one of the other numbers was 12. But you always make me scared when there's something in the chat and it's like it's not what I have. But in any case, let's just keep going. That was question 5. That means 6 is going to be tough. Oh my gosh, what's this? ABCD is a trapezoid with parallel bases of AB being 8. Okay, label, label, label. That's 8. And CD is 14. So that whole thing is 14. Do I want to label yet? Maybe, maybe not. Let's go and see. Point M is the intersection of the diagonals. Yep, that's the intersection of diagonals. Points E and F lie on these bases. Okay. Ah, parallelograms. So this is parallel and that's parallel. I like it. And by the way, I immediately saw parallels. So I'm like, I'm supposed to label the bottom at some point. This thing is 8. And similarly, this thing is 8. Well, in that case, I said the whole thing was 14, or MathCounts said the whole thing is 14. 8 plus 8 is 16, but that double counts the middle. That means the middle is 2. That means it's 2, 6, and 6. Does that make sense to people? Because it's like 8 plus 8 would be 16, but that's because it double counts the middle. And if I only single counted the middle, I get 14. That means that one point of the middle, one count of the middle is just 16 minus 14, which is 2. And with that, I can now erase this and label it better. That's 2, that's 6, and that's 6. And you can see that does add up to 14. Okay, let's keep going. I also have that the area of some trapezoid ABEF. Ooh, this trapezoid. This trapezoid is 60 square feet. What is the area of triangle ADM? Whoa, this thing over here. Okay, so I need to know this particular area. I have some ideas. So let's see. Yeah, so this is like lots and lots of ratios are going on here. So the first thing I'm going to do is I'm going to say this particular triangle is related to the whole triangle, not the whole triangle, it's not really whole, but it's related to this triangle. Okay? I actually care about ADM. But if only I could find out the ratio that this DM is out of the whole DB, then that's the area of the triangle I want. Let me write that down over this way. So the area of the ADM is equal to, if only I could find out MD over BD times the area of ABD. Does that make sense? And the reason is because I can think of this as like a half base times height issue. And the base of the ADM is this piece. And the base of the ABD is this piece. But they have the same height. So if only I could find out that ratio, I'm good. And I think I can. Actually, I can find the ratio right now. I can tell you what it is. It's because this is 8 and this is 14. And there's another pair of similar triangles. Let me just draw them. This. So I have a triangle on top and a triangle on the bottom. They're similar to each other because I have parallel lines, and therefore the angle on this is equal to the angle there, and the angle here is equal to the angle there, and of course the vertical angles are equal. Congruent is actually the word. And that means that I've got similar triangles where the ratio of similarity is like, how do you flip your hand that way? Anyway, I need to flip over and then down. Like that's the similarity. But the important thing is that that side is 8 and that side is 14. That means that this piece to that piece is in a ratio of 8 is to 14. Okay? So what I know is that the BM over DM is equal to 8 over 14. Actually, I don't like to write it this way. I'm going to write it with the colons, because that's even easier. BM to DM is equal to 8 is to 14. Terrific. Because in that case, I can simplify that. That's just going to be 4 is to 7. But once you think of it that way in terms of ratios, that means that the DM, or the MD, or whatever, divided by the BD, that'll be 7 over 11. Did that make sense to people? Because I've got 4 parts here, 7 parts here. So therefore, this as a fraction of the whole thing is 7 divided by 4 plus 7. So that fraction is 7 over 11. Okay, that was supposed to be a times sign. Now, the only thing I need to figure out is the area of triangle ABD. How hard could that be? Let's see. Well, if I need to know that blue triangle's area, I can think about like half base times height. If only I knew the height. Is there any way I could find the height? That would be really convenient. What is the height? Well, I know one piece of information. ABEF, this trapezoid, has a 60 square foot area. Well, now I know that the area is going to be the average of the bases times the height. The average of the bases, 8 and 2. What's the average? 2 plus 8 is 10, so the average is 5. So that means that 5 times the height is equal to 60. Therefore, the height is 60 over 5, which is 12. All right, now we're good, because if the height is 12, now I know the area of ABD, half the base times the height. Half the base is 4. 4 times 12 is 48. Yikes. Okay, that's not very nice. Funny numbers. Double checking. 4 times 12 is 48. Okay, so I guess I don't get to simplify. I need to do 7 times 48. What's faster, doing it or just getting a calculator? Probably doing it is faster. You've seen how fast I am on the calculator. 48 times 7, 7 times 8 is 56, and 7 times 4 is 28. 28 plus 5 is 33, and I'm immediately checking, because 8 is a multiple of 3. Sorry, no, it's not. 48 is a multiple of 3, and this is a multiple of 3 because if I add up the digits, it's a multiple of 3. That's how I quickly check my arithmetic to make sure I didn't make a mistake. So I get 336 over 11. Okay, so let's see what happens. So I think that the answer to the whole question is 336 over 11. And that should be the area of triangle ADM. Let's see if this is right. 336 over 11. It is! Oh, good. And again, I was scared because I saw someone in the chat said, no. And I was hoping that it wasn't talking about me. Here we go. We're on the final last 2 questions that the mathletes get 6 minutes to solve. We have half an hour. Let's see if we can manage to solve them. Question 7, the parabola y equals x squared minus x minus 2 and the line y equals x plus 1 intersect in 2 points. What is the distance between these 2 points? Express your answer in simplest radical form. Okay, so I need to go and figure out where these points are. Well, first of all, I like to just draw a picture. These days, people can use graphing calculators. Actually, on this particular problem, if you had a graphing calculator, you just graph, you find the intersection points, and you find the distance between them. So that is possible, but let's see if we can do it in a more clever way, okay? So I have something in mind. All right, so when I want to draw a parabola, first thing to do is draw the parabola. Yay, that's x squared minus x minus 2. And I'll have some line. But first of all, where are the intercepts? Actually, I can factor this in my head. This is x minus 2 times x plus 1. If you do enough factoring problems, you start to recognize the way you get the minus 2 is that I need to have the last things multiplied to minus 2. And how do I get the minus 1 coefficient? Well, that gives me a minus 2x and a plus 1x. So that gives me minus x. And that means that the intercepts of this, where it intersects the axis, those intersect at x equals, that is 0 when x equals 2 and when x equals minus 1. And yes, that's right. That equals 0 when x equals 2 and when x equals minus 1. So this is at 2 and this is at minus 1. And that means that the graph looks something like this. Ish. The thing might be stretched in a funny way. You might wonder, how in the world did I know that it's going to go under it? Well, because those are the intercepts. Those are the places where y equals 0. Now I also have y equals x plus 1. And that is that it has a slope-intercept form where it goes through the y-axis, the y-axis is hit x equals 0, y equals 1, and it has a slope of 1. Oh, that's nice. Wow. A slope of 1. That means it goes through here. Math counts, you're very nice to me. So this is y equals x plus 1. Okay, it has a y-intercept of 1, a slope of 1, so it just does this. So now I need to know the distance between these 2 points. Well, if I want the distance between these 2 points, actually I have a 45, 45, 90 right triangle. I already found one of them, it's right here. And so I just need to know the other one. I need to know the x-coordinate of the other one. How do you do that? You just set them to be equal. You say like the yellow one equals the green one. Oh, it's nice. Look at that. If I'm trying to find out when they're equal, then I need to know when is x plus 1 equal to x minus 2 times x plus 1. Factoring happens. Because that's x plus 1. Subtract x plus 1 from both sides. Think of it this way. This is 1 times x plus 1. Now subtract 1 x plus 1 from both sides. I get x minus 3 times x plus 1. And that explains why the places where you have these two intersections happening, these intersections are happening exactly at x equals minus 1, which was here, and x equals 3. So that means that this thing comes down to 3. I apologize for my not drawn to scale picture. But now you already can see, if that's 3, wait, no, this is at 3. That means that this is 4. And that means that the height is 4. That's right. So this thing here is 4 tall. This thing here is 4 wide. And therefore, the distance between the 2 points must be 4 root 2, right? Because it's 3 and then y equals x plus 1. So it goes up to 4. So I have a 4, 4, 4 root 2 distance between the 2 points. And I'll put that as my answer. Simplest radical form. I hope this works and no calculator. Yay! And that takes us to the last question. Oh boy, the words got smaller. That means it might be hard. Not including the identity transformation. The 11 transformations that preserve the regular hexagon shown are counterclockwise rotations by 60 degrees. What's a counterclockwise? It's this. Yeah, counterclockwise. Our 60-degree rotation, 120, 180, 240, and 300. And also reflections across these 6 dashed lines shown. I guess if you look really closely, you can see that there are some dashed lines. You can do this reflection, for example, but you can also do reflections like, so this reflection is a reflection where I'm reflecting across something that is perpendicular to a side, but I can also do this reflection, and that one goes through an axis where it's through 2 of the corners, through 2 of the vertices. So there's different varieties of these reflections. Okay. Christina randomly picks 6 of the transformations with replacement. She performs these 6 transformations on the hexagon in succession. The probability that the point P is transformed to each of the hexagon's 6 vertices exactly once during this process is k divided by 11 to the power 6. What is the value of k? What? Okay, so I need to go and find out how can I make P bounce to each of these vertices. All right, let's start to go and take this apart. So what I want to know is I have these 11 transformations I'm allowed to make, and I want to know how far my point P can move during each transformation. Let's do it that way. Because you see, I've got all these different things, and yeah, that's exactly how I'm going to do it. Because then I'm going to say, once I know what P is allowed to do as it moves, then I go and say, is there a way I could get a sequence of moves of P that does a perfect tour of all of these vertices? Okay? So let's see. I should be able to say, how many ways can P get to, it's tally time. Let's do some tallies, okay? Tally marks. So what I'm going to do is I'm going to say there's a bunch of transformations I can do. Let's do all of the counterclockwise rotations first. So P could get here, P could get here, P could get here, P could get here, P could get there. I just did the 5 of these transformations. Now I also have another 6, which are these flips over the dashed lines. So I'm actually just going to go through the dashed lines one at a time. And I'm going to go through them where I'm going to say, let's think of this dashed line first. that dashed line, if I flip the P over that dashed line, then where does it go? It goes here, tally time. Next, what about this dashed line? If I flip P over that dashed line, I get here. Next, you can see how I'm being systematic. I want to make sure I covered everything. If I flip P over that dashed line, it looks like it goes here. What a nice pattern. Next, if I flip P over this dashed line, well, then it's going to drop to the bottom. It'll be here. And if I flip P over this dashed line, then it'll go here. But there's another dashed line. That is this one. Oh, it stays put. Yeah, that makes sense. It stays put. And then after that, I've taken care of all of the dashed lines because this thing here, this is the same one as that one. So now what I've just found out is that if I do one of these random things, so I do 6 transformations, and yeah, okay, I'm reading carefully because it's like I need to do 6 transformations and I need to get back to my start. That's really what's going on because I don't count starting here. It's like, do a transformation, great. And then after you do a transformation, then let's see where you got, okay? So now what I've just found out is P can really fly everywhere, okay? So P can fly everywhere except for itself. P is less likely to land on itself than everything else. So wherever you start from, you're quite likely to land on something else other than your start. So in that case, the way I can think of this is let's just go and think of all of the different possibilities of the order we can land on. Should I have that? Oh yeah, here's how we can think of it. Okay, so the interesting thing here is that going to somewhere else. See, so you can see I'm just staring at this, trying to think. This is a really clever problem. But the way I'll think of it is, from your point of view, you either stay put or you go to somewhere else. Okay? So that's a really important observation here. Each step, what happens is you stay put. And that's a probability of 1 over 11. Or you teleport. And you teleport uniformly random. Uniformly randomly. Uniformly randomly means like where you go, you just go somewhere, okay? And that one is going to be with probability 10 over 11. But the important thing is, how often should you be staying put? Actually, you should probably not really stay put. If you want to go and visit everything exactly once, the only time you're ever allowed to stay put is if you said, my first step is to stay put, and now let's go randomly teleport. Okay? And that's the only place you'll ever use the stay put. I'm breaking into some cases. I'm saying like, what kinds of different ways can I take this random tour? Well, I've got 2 kinds of random tours. I've got I call these like, well, let's call them tours. 2 kinds of tours. The first kind of tour is that you first stay put. And so the first place you go is right back to yourself. You start by stay put. Well, if that's the case, the probability of that is 1 over 11 times. Now what happens? Well, now the whole world's my oyster, or whatever that phrase is. I've got 5 other places to go, and because of the symmetry, I teleport uniformly randomly to another one. I should say to other. Okay? It now doesn't matter what order I do the other ones in, because I'm basically saying stay put, followed by teleport, 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 teleport. Okay? And each of those is going to be a 10 over 11 chance of doing some random teleport. Okay. But now it gets interesting. It's because as I'm doing these random teleports, I do have to think of like what order are the 5 things I'm going to visit in. I have 5 other vertices. So there's a 5 factorial. As I start to take into account that, well, you see, you first decided to stay put. Good for you. Now decide, what order will you go through the other 5 vertices? 5 ways to decide which one you go to first. 4 ways to decide which one you go to after that. Then 3, and then 2, and then 1, and then so on. But now that I've decided, suppose I decided that the path I want to use is I want to use stay put, and then like fly over there, and then fly over there. Oh, fly over there, jump back over here, and then over there. Suppose that's what I chose. Once I dictate that's what I want to do, now the rest of it is just going to be that, well, what's the chance? Well, if I want to go and teleport over to there, it's a 10 over 11 chance that I would be able to jump, to teleport, but I actually want to jump to a very specific one. So actually, not only is this teleport randomly in orders 10 over 11, I actually want to know what's the chance that I land on a very specific one. That's 2 over 11. So what I'm saying is that in this 10 over 11 area, in that zone, the way that I should go and think about this is that I'm going to have, I'm already thinking of a much better way. Yeah, I see how I can explain this in 2 ways already. But let's just do it this way, all right? So let's do it this way. So it's like I have a 2 over 11 chance of landing on that very particular spot. The 5 factorial was to observe that I can go through them in any order. So I should have a 2 over 11 to the power 5. Because I'm always going to be saying go to a different one, and to go to a different one is always 2 over 11. Why I kind of paused is I said, this 5 factorial times 2 over 11, that happens to be the same as 10 over 11 times 8 over 11 times 6 over 11 times 4 over 11 times 2 over 11. That can be done by taking each of the 5 2's and throwing them into each of the 5, 4, 3, 2, and 1. And why I smiled is because you can also think of it that way. You can say, this means I stay put first, 1 over 11. Now I go 10 over 11. But then the next time I go, I need to avoid the places I've already been. So now it becomes 8 over 11. And then I need to avoid the ones I've been to now, which is 6 over 11, and so on. So I was just showing you 2 different ways of understanding why this is probably right. The second option, is you start by going. But once you start by going, you gotta keep going. You can't say like I go and then I decided to stay put. No, then you hit twice there. Right? So if you're going to go, the first thing you can do to go is, that's a 10 over 11. But now once you decided to go, let's erase this purple stuff. In case you came late, these are not 11s, these are tally marks. Those are all 2's. Okay? So once you decided to go, now it's just going to be go, 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 go. And actually, again, the way to think of it is, where do I go first? Well, I don't know. I could go anywhere. And that's why this 10 over 11, it drops me to anywhere. I don't know which one of them I happen to be in. It's just an anywhere. Now, once I landed into an anywhere, I now have to say, I'm somewhere. Who knows? Maybe it's here. I have 5 other places that I could go to. And I'm saying it should look just like that. It's like you've gone to an anywhere. And after you're at an anywhere, now you can have 5 factorial ways that you visit the rest of the stuff. Okay? So that's 5 factorial ways to visit the rest of the stuff. And for each of those steps, as you go visit the rest of the stuff, is 2 over 11 to the 5th that your teleport goes to the right spot. And the other way you could think of this is you could say, well, I start from the P. 10 over 11, go anywhere. Great. Now I'm anywhere. Now I can just do another 10 over 11, go anywhere. Great. Oh, but now as I'm going to do a go anywhere, I have to avoid that one. That's why I have 8 over 11. So that's why the answer is also 10 over 11 times 10 over 11 times 8 over 11 times 6 over 11 times 4 over 11 times 2 over 11. Okay, so that's the answer. And I need to add this all together. I need to know what is k over 11 to the 6. Oh, look at that. There's 11 to the 6 there. So the answer to the whole thing is 5 factorial times 2 to the 5th plus 10 times 5 factorial times 2 to the 5th. Right? Oh, that's nice. Wait, is it that nice? I see a multiple of 11. Why did that happen? Now I'm a little suspicious, because why did MathCounts ask me over to 11 to the 6th? So I'm just double checking to make sure there's not some error here. Because like 1 over 11 times that and 10 over 11 times that, those add up to the same thing. But that sort of makes sense. That's saying that the first move, do whatever you want. Yeah, so the first move, you should do whatever you want. In the first move, you just do whatever you want, right? And in the first move, after you're wherever you want, you are somehow on a spot. And now you're on a spot. Now you say, I'm never allowed to stay put again. So now I need to go visit everything else. And that would be the rest of this. Okay, so then the answer to the whole question, if I add these together, it'll be 11 times the numerator. So the answer to the whole thing should be 11 times 5 factorial, which is 120, times 2 to the 5, which is 32. Okay, I guess here comes the calculator. All right, 11 times 120 times 32 equals, wow, 42, 240. Okay, so I think that's the answer. Let's see if this is right. I quickly checked, is that a multiple of 11? It is. If this multiple 11 thing is like, you can take the digits which are on the even positions and the odd positions, whatever even and odd means. But it's just like like this digit 0 plus the 2 plus the 4, that should be the same as the 4 plus the 2. That is a multiple of 11. All right, let's see if this is right. 42240. It is. Okay, we managed to do it. Now let's go back and look at it. Because I mean, I saw some people said they're confused. And so this is the hardest question on the entire set. And we did manage to get it right. So then I can just like take a look again and see what exactly happened. For this particular problem, the whole idea was just observing that the whole point of looking at this problem is that you somehow have to first understand from any point, where could you be after one of these transformations? And what we found out is, from that point, where you could be is anywhere, but it's like a little bit less likely that you're at the same spot as where you started. And once we found out that it was symmetrically distributed of like the anywhere that you could go, that made me really happy. Because then the way I can think of this problem, eventually we noticed that these two boil down to the same thing. It's just that, hey, go teleport anywhere you want or stay put. Whatever you want, the first round is free. Now, once you decided where you are, notice that the only way to visit everything exactly once is to never sit on your same spot again. And then the game became, all right, well, given that I'm equally likely with 2 over 11 chance to fly to any other particular place, that's why there are 5 factorial ways to order the rest of the places I might go to, times a 2 over 11 chance of making each flight go to the exact spot. And it works. Okay, so actually it worked. And that finishes the math counts. We actually finished. Amazing. Well, that gives us like about 13 more minutes to answer random questions. So I hope that this last explanation made sense. All of these like probability and combinatorics things are tricky because it's very easy to count things wrong. That's why you see that I very carefully wrote things down. I very carefully laid out the possibilities and made sure I didn't double count. If you have random questions you want to ask, they don't have to be about the exact problems we did today. They could be about all kinds of things. We will use the last 13 minutes to start, answering questions that people might have. Somebody asked when the probability module will be finished. I'm working on all of these things as well as the stopping COVID. So hopefully very soon. I mean, the teaching I've been doing right now has mostly been doing things like collaborations with math counts. But because COVID is hopefully going to end soon, we will be able to have more time to go back to teaching again. How are you today? I'm very good, thank you. Particularly because this last question managed to get solved. Skylar, sure, you know I like bananas. Yes, I do like bananas. Some person has asked how many more AMAs will there be until another collaboration? I lost count. I think we'll probably have an AMA next weekend, an Ask Math Anything. These are things that I do every Saturday night, which when we don't have one of these collaborations. But we'll probably have some more collaborations soon. Those are just always advertised on the main page. More questions. When am I going to wear a green shirt? Probably not for a while, but I mean, for a while, let's work on the math stuff first, and at some point we can go and celebrate that we've achieved a lot of things. But right now I'm going to work on the teaching of the math, and also a lot of these live stream collaborations. I think those are really worthwhile. Other questions? Why did you decide to follow a career in math? It's because I like solving things, and I like thinking about things where you can sometimes come up with a really interesting idea that makes a hard thing easy. In fact, that's just what I like. As you can see, I groaned whenever I went to get a calculator because that's not the interesting part. To me, the interesting part is how do you get this to work? Is there any clever trick I can make up myself? Not like a clever trick I remember, right? And once it gets to the calculator, then I'm like, oh no, now I have to punch all of these things in, and it just becomes a mechanical part at the end. This is no criticism of math counts, by the way. I think it's reasonable that people need to learn to use calculators too. But I chose to be a math person because I wanted to think about new ways of doing things. And then, with the math, I got the chance to go and do all this teaching as well. Oh, somebody doesn't know what I'm doing on COVID. If you just go and search for Novid, which is COVID with an N, then you'll find an app that I've been working on with the team for over a year. It's just Novid, novid.org. We invented a new way to fight disease, and that's actually quite exciting. That uses mathematics. More questions. Oh, interesting. So somebody has said, deep geoty, from where to study geometry transformation things like homothety, inversion for Olympiad, except Evan Chen as its cost is too high. So I actually learned a lot of math, not necessarily from using books, but I actually would often think about problems myself. And I would often just use the fact that solutions are out there. You mentioned that some various things that you're looking at, the cost is too high, but the old problems are always around. And so I generally learned a lot by working on old problems and thinking about them. And if I couldn't see them, then I would go and check the answer and try to see how the solution worked. And that's the way that I invented my own ways of doing things. In fact, I often didn't think of it as, I didn't think of it as wanting to learn a technique that other people were teaching so I could do problems with that technique. I was more interested in just developing the skill to invent a technique. For example, like this question, you can't find this question anywhere. This is not the question you can train for. That's why it's so interesting. But it's much better just to learn how to come up with things. Okay. Some person asked, when's your next banana meal? Well, I'm going to have a banana for breakfast. I often have bananas for breakfast. But when's my next banana meal, meaning just bananas? That usually happens when I go traveling, because I might end up being too late to do something, and I'll just eat bananas on the way, and that's the entire breakfast. But I haven't been able to travel for a while because of COVID. Tsihan has asked, which math contest did you take part in when you were a kid? Which do you recommend? Well, we're here at Math Counts for a reason. It's because Math Counts was the competition that I participated in middle school. In elementary school, there was some local math competition, not at all national at all. And that was a lot of computation stuff, like calculation things. And that was okay. But it was really the Math Counts that I was amazed by how clever you have to be to solve the problems, like what you just saw here. And so I very strongly recommend that you do participate in Math Counts if you can. And if you can't, you should try to make sure you can. I mean, if you live in America, you should make sure to get your school registered. Then you'll get to play with these kinds of questions. Ooh, Emerald Studios. What do you think is the most important factor in math that catches people's attention? Again, my view on math is not calculation. My view on math is the idea that you can look at a complicated thing and find this really nice way to look at it from a different angle, and suddenly the problem's doable, right? So I think that that's the wow factor. And that's why I went wow when I was doing this problem in front of you, as soon as I saw the symmetry of, it's different between staying put and teleporting. That's the crux of this problem. Once you realize that it's all equally distributed on probabilities in terms of the teleportation to a different place, life is good. And it's just like these kinds of, find the nice way to break the problem apart. That's I think the most noticeable thing in math. And I've also noticed when you explain to people, if you're teaching people math by saying, here, do this problem, watch me do it, and now you do it too, they don't think it's that beautiful. They're just like, okay, well, you told me to do this and I put some numbers in, so I guess it's doable. But once you show them that you can look at things from different angles and very complicated things become very easy, then it's good. Some person has asked, do you plan on getting better at chess? No, I don't. I think that I enjoy the act of figuring things out, and so I'll play chess with people occasionally, maybe. And I won't really try very hard to get better, because that's just not where I want to drive my energies. I have no problem with the people who do. It's good for you. You find it fun, good for you, go for it. But I personally am doing other things that I find fun. So the chess to me is like, yeah, it's a nice mental exercise, but I don't intend to just practice it just for the sake of practicing it. More stuff here. Somebody said, who's the most, someone, well, you guys have such great names. Who is the most famous person you've met? I mean, I think I don't know. The issue is that at some point when you meet some people, you also have to keep that confidential. So I think I'll give that as the answer. The answer is the most person I've met, I'm not really supposed to talk much about. And that's actually quite standard. Just to give you an idea of why that is. It's because a lot of people like their privacy. So sometimes there are quite impactful people in the world who, as you're working with them, it's actually not very good if it's widely advertised that you're working with this person. So I guess I'll just put a blank on that answer for you. Oh, come on. I'm not that famous. As far as I understand, my Wikipedia article apparently says that his favorite color is blurple. But it's probably one of you who made that. Anyway, okay. Other things. Okay, Tihan, do you have any tips to do well on a timed math contest like MathCounts or AMC? Okay, so if you saw, we didn't do so well on the time here, right? We spent 2 hours doing a 40-minute exam, and then we spent like 45 minutes doing something you have 24 minutes to do. So I'll give you 2 answers to that. The first is, I think that the true value of MathCounts and all these contests is that the questions are legitimately interesting, and you should do them without a time limit during most of the year. In fact, when I coach my local team in Pittsburgh, this is just the school my kids go to, when I coach them, we don't even care about the time limit for most of the year. We just do interesting problems. And we just do the problems that came from MathCounts until we get them done, sort of like this. It's only towards the end, maybe in the last month or 2 months, that we start to pay attention to the time limit. And then what I would say is for a timed exam, what you do is you learn to think faster. And that just comes from stretching yourself, to go and push your brain to think a little bit faster every time. And if you're able to think faster and faster and faster, that helps. But what you'll also discover if you've spent most of the year thinking about how to invent ways to solve problems is that you're also pretty good even at the ones that you have never seen before. So I would worry a bit less about the timed exam and worry a lot more about the thinking process. Someone asks, why do you like blurple? Right? So blurple is like some shade of that, right? Oh, I should actually probably flip to my bigger screen. Yeah, this one. This is the one, because I'm just doing random QA now, right? And so, yeah, I like blurple because it's this very, very satisfying mix of the blue and the purple, which is not quite clear which it is. And maybe that's also something I like about creativity, right? Oh, come on, please. Somebody made some comment about editing Wikipedia page. I do hope that my Wikipedia page doesn't get edited too much, because I think that could make them even pull it. But I will say that the other day, someone was asking me, what is this nonsense on your Wikipedia page? I explained that, I mean, for better or for worse, a lot of my fans are middle school students. And so interesting things happen. Okay, somebody just taught me it's periwinkle. Very nice. More questions. So S. Naguib Ali has asked, do you have a favorite theorem or proof? Yes, I do, actually. But I mean, you may know this. I think that there's a most beautiful equation in math, and that happens to have the 5 numbers in it, the e, pi, I, and 0. So if I look at the most beautiful equation in math, this is not just me who thinks it. A lot of people do. If you Google it, Google thinks so too. Well, Google just knows what people are saying. Most beautiful equation in math, that is e to the power of pi times I plus 1 equals 0. 0. Okay. Now, actually, fun fact. The first time in my life that I learned this equation was at MathCounts. It was my MathCounts coach in middle school who one day told us e to the power of pi I plus 1 equals 0, and that's amazing. And the reason is because it uses the five numbers in math that are extremely important. 0, 1. E is this natural log thing, and the more math you do, the more you find out that this is actually more natural than the log base 10. And pi, come on, pi is the ratio of the circumference of a circle to the diameter. Very fundamental. And the I, that's the square root of minus 1. So these are 5 of the most fundamental numbers in math, and they're all put together in one equation. And the surprising thing is they have no right to be in one equation, because pi is like 3.1415926. It just keeps going. It's crazy. It doesn't even have a repeating decimal. I is the square root of minus 1. It's not a real number. E is this 2.71828. It just goes on and goes on. Also, no repeating. Why in the world, if you put these 3 together, would you just get minus 1? they cancel. It's like three chaotic things come together, all cancel each other out, and it all ends up nice. So yes, so this is actually my favorite. The proof, by the way, is quite a bit more sophisticated. I can't do it in like 30 seconds. But if you go look on Google, you'll be able to find some neat proofs. I did give some proofs. I don't know if those are actually on YouTube, but there's a really nice way to explain these things too. Okay. Yes, and somebody pointed out that CMU did make a video, and I actually don't explain why it's true. I'm just talking about that particular equation. But, you know, it's a nice way to end this live stream because it also happens to be something that I learned at a MATHCOUNTS practice in middle school. And who knew, like that, you know, I was just some middle school kid, I learned this equation, and I never knew that someday I would be one of the YouTube videos that talks about this equation. That's just how funny the world is. So hopefully all of you, as you're learning math or learning things from your coaches, you know, pay attention to them. You never know if they'll come in handy. And the world, the time is very funny because history is somehow circular or something, or you never expect when something you've done before comes back to something you're doing later. With that, we've gotten to the end of this particular collaboration that closes the state round, and that's a wonderful chapter to end. That was not meant to be a pun, but that's a wonderful closing for this work that we've been doing with MATHCOUNTS National Competition. Real pleasure and honor to work with them, and I wish all of you the best in all of your learning. I'll see you in the next session.